For this question, we want to determine the difference quotient for the function f of x equals 3x minus 5. This expression here is the expression for the difference quotient. Difference because it has subtraction, and quotient is this fraction bar here. And what we're going to do is we're going to calculate this difference quotient in a couple parts. So we're going to start by figuring out this first part here, which is f of x plus h. So we're going to find this part right here. We're going to find this part, f of x. Then we're going to subtract those two. And then finally, we're going to perform this division. So starting with f of x plus h. What that means is that we want to replace the x in our function with x plus h. So that would look like this. 3 times x plus h minus 5. I want to simplify this. I'm going to simplify using the distributive property. That's going to give me 3x plus 3h minus 5. And none of those terms are like terms, so we're going to leave this as simple as possible, which is what we have, 3x plus 3h minus 5. So that's this part here that we've just figured out. Then we've got f of x. Now f of x is what was given to us as our function, so there's not really any calculation needed. We just need to recognize that f of x is 3x minus 5. So then we're going to perform this subtraction. So we want to do f of x plus h minus f of x. We've already figured out f of x plus h to be 3x plus 3h minus 5. And we want to subtract f of x, and f of x is 3x minus 5. I need to put parentheses around that 3x minus 5 because I want to make sure that this minus sign applies to the whole function. So I need parentheses around that 3x minus 5 to make sure that that minus sign applies to the whole function and not just the first term. So then I can do the distributive property. And I've got 3x plus 3h minus 5 minus 3x plus 5. So that's applying the distributive property. And now I've got some stuff that's going to cancel out. 3x and negative 3x are like terms, and when you add those together you get 0, so they cancel each other out. And then I have negative 5 and a positive 5, those are like terms, and when you add them together they zero out. So that's going to leave me with 3h. And there's nothing really else I can simplify. So then in my final step, I'm going to take care of this division. This is dividing by h. So for my example, I want to do f of x plus h minus f of x. I'm doing the final step, which is dividing by h. I've already figured out the entire numerator to be 3h. And I want to divide by h. Those h's cancel, and that simplifies to be 3. So the difference quotient for f of x equals 3x minus 5 is 3. For this question, we want to classify the given function as polynomial, rational, or root, and then find the domain. We want to write the domain in interval notation. The function that we're given is f of x equals 9x minus 5 over 9x plus 5. Now I already know that this is a rational function. Now the rational functions are the functions that follow this format where you have p of x over q of x. So meaning that our rational functions are the ones that are in fraction form. Now we do have the specific rule that the numerator needs to be a polynomial function and the denominator needs to be a polynomial function. But honestly, that doesn't matter when we're finding the domain. We find the domain in the same way when there's a variable in the denominator, whether it's a rational function or not. So when you're looking for rational functions, you're looking for a function that has a fraction, that has a variable in the denominator. So the way that we find the domain is by setting the denominator equal to 0 and solving that equation. The reason why we do it that way is because rational functions have fractions, and 0 is not allowed to be in the denominator of a fraction. 0 is a restriction. Division by 0 is undefined. So because we cannot divide by 0 and that's undefined, we have to exclude that from the domain. So we're going to take our denominator, which is q of x, and set it equal to 0, and that's going to help us come up with our restricted values and which values need to be excluded from the domain. So for this example, q of x is our denominator, 9x plus 5. We take that denominator and we set it equal to 0. So remember, 0 is not allowed in the denominator. So we're setting the denominator equal to 0 to find those restricted values. So then I'm going to solve. I'm subtracting 5. I've got 9x equals negative 5. Then I'll divide both sides by 9. And we get x equals negative 5/9. This is our restricted value. So this value, if we substitute it into the function, will cause a 0 in the denominator. Let's actually see it. If I try to do f of negative 5/9, that would be 9 times negative 5/9 minus 5. 9 times negative 5/9 plus 5. These 9s would cancel out, and you have negative 5 minus 5 over negative 5 plus 5. Negative 5 minus 5 is negative 10. Negative 5 plus 5 is 0, and there you have division by 0, which is undefined. So this value of negative 5/9 is a restricted value. It causes the function to be undefined and therefore cannot be in the domain of this function. So then we want to write the domain in interval notation. So what I like to do is to draw the number line. The number line goes from negative infinity to positive infinity, covering all real numbers. And we have this one restricted value of negative 5/9. So I'm going to mark on the number line that restricted value, and I'm marking it with an open circle. We use the open circle to indicate that that is not part of the set. And we're going to shade the rest of the line. Our only restricted value is -5/9. And then we want to write down the interval notation. When you write interval notation, you write a lower bound, comma, and upper bound. And then you either use parentheses or brackets on the left, parentheses or brackets on the right. So I need to represent this interval. And this interval will start at -infinity and stop when we get to the restricted value. So our lower bound is -infinity and our upper bound is -5/9. So that interval is -infinity to -5/9. And I'm using a parenthesis on this because the parenthesis has the same meaning as the open circle. That number is not included in the set. So then I'm going to do the other interval. And the other interval has a lower bound of our restricted value and an upper bound of infinity. So this other interval starts at -5/9 and goes to infinity, and then we're going to union those two sets together. So this is our domain, -infinity to -5/9, union with -5/9 to infinity. So this is saying the same thing as all real numbers except -5/9. On this example, we want to find the x-intercepts of the graph of the function without graphing the function. Our function is f of x equals the square root of x plus 11 minus the square root of x minus 1. And we want to find the x-intercepts of this function. Whenever we're looking for an x-intercept, the x-intercept is where the graph crosses or touches the x-axis. And because it crosses or touches the x-axis, the y part will be 0. And so that's how we find x-intercepts, is by letting y equal 0. Now our equation here is written in function notation. So f of x represents y. So we're going to let f of x equal 0. So we have the equation 0 equals the square root of x plus 11 minus the square root of x minus 1. And this is what we call a radical equation or a root equation. The strategy that we're going to use to solve this type of equation is to isolate the radical and then get rid of the radical. So I'm going to start by adding square root of x on both sides. And I'm adding square root of x so that I have that radical isolated. So now I have this radical, square root of x, isolated on one side of the equation. Once you have it isolated, then you're going to get rid of it. So the way you get rid of a square root is to square. I'm going to square the left, and whatever you do to one side, you have to do the same thing to the other side. So you square the right, and the square and the square root will cancel each other out on the left. So we're just left with x. On the right, it's going to get a little bit messy. We are squaring a binomial. So I'm going to write it twice. because that's what squaring means. Squaring it means multiply the base 2 times. And then I'm going to multiply it out up here. We have x equals, and we're going to multiply these first two together. Square root of 11 times square root of 11. Excuse me, I misspoke. That's square root of x plus 11 times square root of x plus 11. That's x plus 11. Then I want to multiply the outside 2. That's square root of x plus 11 minus 1. That's minus 1 square root of x plus 11. Then I want to multiply the inside 2. And that's minus 1 square root of x plus 11. And then finally, I want to multiply the last 2. That's negative 1 times negative 1, which is a positive 1. So before I go any further, I want to make sure you understand how we got each one of these parts. So let's pause on this part right here, how we got x plus 11. I'm going to write up here, we're multiplying square root of x plus 11 times square root of x plus 11. And that's equal to the square root. Now when you multiply square roots, you multiply what's underneath them. So that's the square root of x plus 11 squared, and then the square root and the square cancel each other out. So that's how we got x plus 11. Then let me check to make sure that you understand how we got this part. When I multiplied x plus 11 times negative 1, one of the numbers is in a square root and one is out of the square root. And those don't mix. So like on this one, both of these were inside a square root, so we multiplied them together. But when one's on the inside and one's on the outside, we leave them that way, just like we have it here. So that's how we got that one. All right, so with that cleared up, I'm going to continue. And I'm going to start combining like terms. So I've got a positive 11 and a positive 1 that will combine together. That's x plus 12. And then these two terms, we call these like radicals, sort of like terms. And when we combine those together, we're going to have minus 2 square root of x plus 11. And so we have, at this point, accomplished getting rid of this radical right here. However, we still have a radical in the problem, so we have to repeat that process over again. We isolate the radical and square it to get rid of it. So I'm going to subtract x on both sides. That's 0 equals 12 minus 2 square root of x plus 11. I'm going to subtract 12. So negative 12 equals negative 2 square root of x plus 11. And then I'm going to divide both sides by negative 2. Negative 12 divided by negative 2 is positive 6. And now I've isolated this radical. Once you isolate it, then you try to get rid of it. So to get rid of this square root, I'm going to square. I'm going to square the left and also square the right. The square root and the square cancel each other out, leaving me with x plus 11 on the right. 6 squared is 36. And then I'm going to subtract 11 on both sides. That gives me x equals 25. Now, seems like we've got our answer. but there's one more thing that we have to do. And it's because of us doing this step where we square both sides. It's possible that when you square both sides that you get what we call extraneous solutions. These are extra solutions that don't work in the original equation. So what we have to do is we have to check to make sure that we don't have one of those extraneous solutions. So we're going to check our proposed solution of 25. We're going to check that x equals 25 in the original equation. So I'm checking it in this equation right here. So our equation is 0 equals square root of x plus 11 minus square root of x minus 1. I'm going to substitute 25 everywhere I see an x. That's 0 equals 25 plus 11 minus square root of 25 minus 1. Square root of 25 plus 11. 25 plus 11 is 36. Square root of 36 is 6. Square root of 25 is 5. And I have 6 minus 5, which is 1, minus 1, which is 0. So this is a solution to our equation. And so we're going to keep it. And this is our x-intercept. We have an x-intercept of 25, 0. Thank you for checking out my videos. Have a great day.